Okay, this is Unit 4, which is all about transformations, and this is our first lesson, which covers reflections. And we kind of got an introduction into reflections in the Sketchpad activity that we did in class the other day, but we're going to look at some of the specific things that you're going to need to be able to identify and put together with reflections. So our learning goal for this particular lesson is that students will understand, use, and construct reflections of plane figures. Now right here where we're talking about plane figures, we're not talking about ordinary figures. When we say plane, we mean figures in the plane. So in other words, flat surfaces. Okay, so our success criteria for this is we want to be able to identify a transformation that is a reflection. We want to be able to identify the corresponding sides between what we call a pre-image and an image, and so we'll talk about what those two things mean, an image and a pre-image. We want to be able to construct the reflection of a figure in the coordinate plane when it's reflected over a horizontal or vertical line. And then we also want to be able to construct a reflection of a figure in the coordinate plane when the figure is reflected over any line, not necessarily a horizontal or vertical line. So let's talk about transformations and what we mean. A transformation is just any kind of change in position, right? So we're transforming a figure. So it might be changing its position, we might be changing its shape, we might be changing its size. Now for the most part, the transformations that we're going to look at aren't really going to be changing the shape of the figure as much as they will be either changing the position of the figure and changing the size of the figure. Now, once we have that transformed figure, once we change it a little bit, that new figure is called the image. It's kind of like when you take a picture of somebody, that picture is an image of the actual person. The actual person we would call the pre-image. So this is the figure before we do any transformation, we call the pre-image. So let's think about the appropriate columns that would go on the left here. How about what is a transformation, right? Strict level 1 vocabulary question. And let's make sure we also have in here what's the difference between an image and a pre-image, because that's what we're focusing on in these vocabulary words. So pre-image is the original figure. Image is what happens after we transform it in some way. So let's think about a couple of examples of different kinds of transformations that we might have. And I don't know, just an interesting way to think about it might be to consider these different puzzle pieces, right? Sometimes when you're working with a puzzle, you might need to take a puzzle piece and move it from where it was to where it needs to be. So you might just pick it up and slide it somewhere else, right? But another thing, I don't know if any of you have seen those crazy puzzles that actually have images on both sides of the puzzle piece. And so one thing you might need to do is actually flip that piece over in order to get the part that you want to make it fit where you want it to fit. So the figure might also flip. Another thing that you might need to do with a puzzle piece is turn the puzzle piece, right? Sometimes it's not in the orientation that we want it, so sometimes we have to turn it around to get it to fit. Now something that we don't really do with a puzzle is change its size, right? But you can see that this one is way too big to fit in the space that I have for it here. So maybe I need to change its size in some way. And in this case, I have to kind of change it in a couple different dimensions in order to get it to fit where I want it to fit. But that's basically all there is to doing these transformations. We're going to slide them. We're going to flip them back and forth. And we're going to rotate them or turn them, and then we're going to change their size. Even when we change the size, the figure itself doesn't really change what the figure is, but its similarity ratio is going to be a big part of how we change its size. So a question that we could look at over here are what are the 4 different transformations? Slides, flips, turns, and a change in the size. Okay, here's another vocabulary word, isometry. An isometry is just a transformation where the pre-image and the image are congruent. So some transformations will result in an image that's congruent to its pre-image, and some of them won't. If they are congruent, we call that an isometry. So which of the previous transformations that we just looked at were isometries? So what is an isometry is a great question to put on the left here. But let's think back to what we just did a second ago. Is a slide an isometry? Sure it is, because all we did was pick up the figure and moved it somewhere else. We didn't change its size at all. Is a turn an isometry? Again, it is, even though the orientation of the figure is changing. The figure itself is not changing size, so a turn or a flip would be an isometry. A turn would also be an isometry, again, because we're not changing the size of the figure at all. The only thing that wouldn't be an isometry is this last one that we did, that we had to enlarge or reduce the puzzle piece. So the first three were isometries. Now let's talk about notation. There's a lot of different types of ways that we can use mathematics to write about transformations or moving figures. And another vocabulary word that we use is maps. So a transformation maps a figure onto its image. And all that means is it's telling us how to move the figure. So when I say this maps, it's just telling me what to do to the figure. Where do I move it? How do I turn it? How do I flip it? What is it that I do? So when we have an arrow is indicating a mapping. It's saying, take this original thing that's over here and put it, or do this to it so that it moves somehow. Another piece of notation is called prime notation. And prime notation is just when you take a letter that represents a point and you put an apostrophe after it. But we read that out loud as A prime. And prime notation is used in all sorts of different fields in mathematics. It's used to describe transformations. It's used in probability. It's used in calculus. It's used all over the place. But in this case, what it's talking about is that the point A maps to the point A prime. So it's kind of like what happened to the original point A? Where did it go? Point B maps to point B prime. So it's just telling me where the points A, B, and C go. So another way that we could say this statement right here is that triangle ABC maps to triangle A prime, B prime, and C prime. So that's kind of some of the notation that we're going to use when we're talking about transformations. So a good left-hand column question here is about that. What notation do we use to indicate a transformation? And so that would be the arrow. All right, so I specifically want to talk about reflections in this lesson. So another way we describe a reflection is a flip. You're just flipping something over. Okay, so another name for a flip is a reflection. Now there's a few properties of reflections. The first property is that a reflection reverses orientation. And what I mean by orientation is the order that the points occur in. So for example, I think this is easiest to describe with an example. If triangle BUG has a clockwise orientation, in other words, if I start at B, I'm going to go in a clockwise direction to get to the other point. So B, U, G. I'm traveling in a clockwise direction here. B, then U, then G. But if I flip it, if I create a reflection, now that orientation is going to be counterclockwise. If I start at B prime to get to U prime, I have to go in the counterclockwise direction. So we say that it reverses the orientation whenever we have a reflection. So that's one of the properties. Another property of a reflection is that it is in fact an isometry. And all of this means is that triangle BUG is exactly congruent to triangle B prime, U prime, G prime. Okay, so let's fill in our questions on the left. What's another name for a flip? Oh, we got that one. And then, is a reflection an isometry? Yes, it is. The only thing it changes is the orientation. It does not change the size. All right, so let's talk about how one of the things that we have to have for a reflection is the reflection line. And this is kind of a part where we have to be careful about how we say things. What we say out loud is that a reflection in line R is a transformation where if a point is on the line R, then the image of A is exactly equal to itself. In other words, A is equal to A prime. If a point B is not on line R, then R, that's the line, is the perpendicular bisector of the segment B, B prime. Now, that sounds kind of complex, so let's break it down here. What this is saying is that if we have line R, like we do here, this is our reflection line. That's kind of the line that something is reflected over or folded over, right? If we have a particular point A, and that point A happens to be on the line R, then that point A is going to be exactly equal to A prime, because both points are exactly on the line, so they're equal to each other. It doesn't move because it's on the reflection line. But if we had point B, like we have right here, B, right here, if I reflected it over line R, I'd be basically folding, if this were on a piece of paper, I'd be folding the paper along that line, and then where that new point matched up with would be the new transformed point, B prime. Now it turns out that if that happened, if you connected the segment from B to B prime, this reflection line R would be the perpendicular bisector of this segment B, B prime. And that means that these two little segments right here are congruent, and this is a 90-degree angle. So that's one way that you can actually tell if a figure has been reflected over a line, is looking for those congruent segments and those 90-degree angles. All right, so nice question that goes on the left here. What properties does a reflection line have when a point is on the line? Well, then the image is equal to the pre-image, so they're the same point. And if a point is not on the line, then the segment that connects the image to the pre-image is bisected by the reflection line. All right, let's do a couple of examples to talk about what this is really going to look like in problems that you have to do. So let's say that triangle ABC has vertices A, which is at -3, 4, B, which is at 0, 1, and C, which is at 2, 3. And then we reflect that over the x-axis. So what we want to do is draw the triangle and its image. Remember that triangle ABC here would be called the pre-image. That's the original figure. All right, so let's scroll up here so we have a little bit of room. So A is at the point -3, 4. Need a real pen here. Let's do blue. So -3, 4 is that point right there. B is at 0, 1, and C is at 2, 3. So those are all my original points, and then what we want to do is connect them so we can make our triangle ABC. And another thing we might even want to do is label those points. So we had point A, B, and C. So A was at -3, 4, B was at 0, 1, and C was at 2, 3. So if I want to reflect these lines over the x-axis, it's as if I took my paper and folded it right along the x-axis. And if I folded my paper in half along the x-axis, where would these points line up with? Remember, the reflection line has to be the perpendicular bisector of the segment that connects a point, a pre-image, to its image. So if this is a perpendicular bisector, then draw a perpendicular line from A. Oh, it's really hard for me to draw a perpendicular line here. Oops, let's get C back there. You can see that perpendicular line would come right down like this, and it's going to be exactly equal on both sides, right? So I hope you guys can see this. We'll go over it in class, make sure it makes sense. A prime would be here at 3, -4. B prime would be at 0, -1, and C prime would be at 2, -3. And then all we need to do is connect those dots again. So let's make this red just so it's a different color here. So connect the points. And does it appear that this triangle has been reflected over the x-axis? It does. We got one more thing to do though. We need to label our points. A prime, B prime, and C prime, so we know that those are the transformed points. So A prime would go here, B prime would go here, and C prime would go there. So that's one of the things that we need to be able to do. Reflect a triangle or another figure over the x-axis, or maybe even over the y-axis, which we'll do next. Okay. So let's reflect that same triangle over the y-axis. So remember what our points were. Negative 3, 4, 0, 1, and 2, 3. So let's start by plotting those points. Negative 3, 4. Oops, let's make that bigger. Negative 3, 4, 0, 1, and 2, 3. And then connect the dots. There's our triangle. And then, of course, we want to label it A, B, C. All right, so bear with me here. A was there, B was here, and C was here. Now this part gets a little weird because we want to reflect this triangle over the y-axis. So here's what I want you to consider. Pretend that these segments weren't actually here. I'm going to group these and I'm going to just take them away just for a second. I want you to consider each individual point. If you took the point A and you reflected it over the y-axis, where would it end up? Well, it's 3 units away from the y-axis, so if we go 3 more units, my new point A would be right here. So let's label that A prime. Maybe we'll even make it red so we can really tell. All right, so here's A prime. Well, what about point B? If we took point B and reflected it over the y-axis, it wouldn't move at all because B is already on the y-axis. So it's 0 units away from the y-axis, so it's going to stay right on that reflection line. And then if we look at point C, C is 2 units to the right of the y-axis, so if I reflected that, that's going to end up, whoops, 2 units to the left of the y-axis, right over there. So let's label that one as well. We'll call that C prime, and we'll make it red. Now the reason that this one is more difficult to visualize or looks a little bit weirder, because when you actually go ahead and put your triangles back in there, your triangles are going to overlap. So now let's make our second triangle A prime, C prime, A prime, B prime, C prime. So this one looks like this. So having both triangles in there at the same time as when you make your drawing can be kind of confusing. So visualize what it looks like without the segments of the triangle drawn, and it'll make it easier to reflect a figure that overlaps on itself. Okay, so how do you reflect a figure over the y-axis? All right, one last example. What if you have this? If you want to reflect a line or a figure over the line y equals x, what you're doing is you're taking that figure and you're reflecting it over the line y equals x plus 0, right? The x-intercept or the y-intercept is 0, and the slope here is really 1. So that line looks like this. And when you do that, what you're really doing is reversing the coordinates of your figure. And so this is really important. I want you to write this down in your notes. Reflecting a figure over the line y equals x, put this in a box, make it red, highlight it, I don't care, something like that. You need to swap the coordinates or reverse the coordinates. And in fact, make sure you have this question on the left-hand side as well. How do you reflect over the y equals x line? So what we need to do is figure out, well, what are the coordinates that we see here? So we'll take them one by one, right? So for example, this coordinate right here is the coordinate negative 1, 2. So if I reverse that coordinate, I'm going to get the coordinate 2, negative 1. So that's right there. In fact, let's put those coordinates in here just so we can have a couple of examples of what we're talking about. The coordinate of the pre-image was negative 1, 2. And then the coordinate of my image was 2, negative 1. we reverse those coordinates in my transformation. Make it a little bit smaller so we can squeeze it in here. -1, 2. And then this one got moved to 2, -1. So let's figure out what the rest of those coordinates are so we can plot them. This one was -2, 1. So that one's going to move to 1, -2. This one up here is -1, 4. So that's going to move to 4, -1. And then the last vertex here is -5, 4. So that's going to move to 4, -5. And then all we would have to do is connect the sides of my figure. What you want to focus on when doing this is looking for the vertices of your figure. Once you find the vertices, plot them, and then you can connect them with the side segments, or the segments that make up the side. Now if you look at this, it really does look like if I folded my paper along this dotted line, those two figures would match up. Now this is one of the things that you have to write in your notes and use as an example. When you want to reflect specifically over the line y = x, what you need to do is reverse the coordinates of your points and plot them and then connect the sides. If you wanted to reflect a figure over a different line, it's a little bit more complex, but it's the same idea. And you want to utilize the fact that the reflection line is the perpendicular bisector of any of the segment that connects any point, any pre-image, to its image point. So you can see here, if you look at this black line that I just drew, this reflection line is perpendicular to it and it cuts it exactly in half. So that's going to be one of the activities that we do in class, is actually practice trying to reflect something over a different line than these three lines that we've looked at in the notes today. So what I want you to do now is use your notes to try some of the practice problems that we looked at. I want you to write your summary, which should include what is reflection. It should talk about an isometry, and it should talk specifically about how to reflect over the x-axis, the y-axis, and then also the line y = x.